I welcome you all for this third lecture on system of linear equations. In this lecture, I will discuss following topics: Gauss elimination method in matrix form, existence and uniqueness theorem for a given system of equations, Gauss-Jordan method, homogeneous system of equations, and system of linear equations and linear combination of vectors. Consider the following system of three equations in three variables x, y, and z. We have these equations: x minus 2y plus 3z equal to 9. Second equation, minus x plus 3y equal to minus 4. Third equation, 2x minus 5y plus 5z equal to 70. So for this system, we can write down the associated augmented matrix as AB. First column is the coefficients of x in these equations, 1, minus 1, 2. Second column represents the coefficients of y in these equations. These are minus 2, 3, minus 5. Third one is 3, 0, 5. These are coefficients of z in these equations. And the fourth column is the right hand side vector, 9, minus 4, and 17. Now we apply elementary operations and we reduce this augmented matrix in echelon form. So I'm writing the matrix here, augmented 1. In the first row, first entry is 1, it is non-zero. So this is the pivot element. Now we make all other entries in first column except the first one, 0. So for this one I am applying the operation, change second row to second row plus first row. In this way, we have the first entry in second row as 0. So we have the second matrix on the slide. First row as it is, 1, minus 2, 3 and 9. And now second row is 0, 1, 3, 5. Third row I am writing as it is. Now we make the first element in third row, which is 2, as 0. So for this one I am applying the following elementary operation. Change third row to third row minus 2 times first row. If we apply this operation, we get the matrix as first two equations as it is, 1, minus 2, 3, 9, 0, 1, 3, 5. Now the third equation is represented by the third row of the matrix. It is 0, minus 1, and minus 1. Now we move to the second row. The first non-zero entry is in second column. This was a 1. So this is the pivot element. Now we use this pivot element and we make the first entry in the third row, that is minus 1. First non-zero entry, we will make this 0. And for this, I am applying the following elementary row operation. Change third row as the sum of third row and second row. So we have third row as 0, 0, 2 and 4. So applying these three elementary operations, the augmented matrix reduces to the last matrix on the slide, which is 1, minus 2, 3, 9. Second row is 0, 1, 3, 5. And third row is 0, 0, 2 and 4. So finally, we have the augmented matrix in echelon form, and corresponding to this we have three pivot elements. In the first row 1, second row again 1, and in the third row we have 2. So I can say that rank of this augmented matrix is 3, as well as the rank of the coefficient matrix, that is the starting 3 by 3 submatrix, is again 3. Now we can write down this augmented matrix in form of equations. So we have following equations now: x minus 2y plus 3z equal to 9. From the second row we have y plus 3z equal to 5, and from the third row we have 2z equal to 4, which implies that z equal to 2. Now we use back substitution and we can find out the values of these variables. So z is 2. Now using z as 2, we can use the second equation and we can find out y. Y plus 3z equal to 5. So this implies that y is equal to -1. We can substitute the value of z. Now z is 2, y is -1. Now we use the first equation, that is x minus 2y plus 3z equal to 9, and from here we get x equal to 1. So finally this system has a unique solution, and it is given by x equal to 1, y equal to -1 and z equal to 2. Consider this example. We have a system of 4 equations in 4 unknowns x1, x2, x3 and x4. I can represent this system of equations by its augmented matrix, that is A, B. First equation I am representing by first row, and this one is 0, 1, 1, -2 and -3. Now second equation is represented by second line, that is 1, 2, -1, 0, 2. Third equation is represented by third row, that is 2, 4, 1, -3, -2. And the last equation is 1, -4, -7, -1 and -12. Now we start with the first row, and its first entry in this row is 0. So this can't be the pivot element. And if we have 0 as the pivot element, in that case we can't make all other entries 0 below this using this 0 non-entry. So we have to do a little bit of calculation here. So what I'm doing, just interchange first row with any of the rows having a non-zero entry. So in the augmented matrix, interchange first and second row. Then we have the following augmented matrix. You can see the first row. It is actually the second row in the previous matrix given on the previous slide. So we have finally 1, 2, -1, 0, 2 first row, and second one is 0, 1, 1, -2 and -3. Remaining third row and the fourth, they are same. Now I can start with the first row, and its first entry is 1, which is non-zero. So this is the pivot element. Now using this 1, I will reduce all the entries to 0 in the first column. So for this one, I am applying following operations. Change third row to third row -2 times first row, and for the fourth row we change this to R4, that is the fourth row minus first row. I am not applying any operation on the second row because its entry is already 0. So using these two elementary row operations, we have the next matrix. 1, 2, -1, 0, 2, first row as it is, second row as it is. Now third row is 0, 0, 3, -3 and -6. Now after applying the second elementary operation, that is R4 to R4 minus R1, that is fourth row minus first row. So we have the last row as 0, -6, -6, -1 and -21. So after applying those two elementary operations, the augmented matrix is equivalent to the first matrix on this slide. Now we move to the second row, and the pivot element here is 1. Now we use this entry and we reduce all the entries below this 0. In the third row, second entry is already 0. So we move to the fourth row. The second entry is -6. Now we reduce this to 0. For this, I am applying the following elementary row operation. Fourth row goes to fourth row plus 6 times second row. After this operation, the fourth row reduces to 0, 0, 0, -13, -39. Now we move to the third row. The third entry in this is non-zero, which is 3. So this is the pivot element. Now we can make this entry as a 1, or we can work with 3 also. So I'm making it 1 here. because 3 is common in third row. So I am applying the following elementary row operation. Change third row to third row divided by 3. And in the fourth row, the pivot element is minus 13. So I can divide fourth row by minus 13 also. So finally we have the third matrix on this slide. And we have first row 1, 2, minus 1, 0, 2. Second row 0, 1, 1, minus 2, minus 3. Third row 0, 0, 1, minus 1, minus 2. And fourth row is 0, 0, 0, 1 and 3. Now the augmented matrix is equivalent to this one, and this implies that the system of equation can be written as these 4 equations: x1 plus 2x2 minus x3 equal to 2, x2 plus x3 minus 2x4 equal to minus 3, x3 minus x4 equal to minus 2, and x4 equal to 3. Now we use back substitution method. From the fourth equation, x4 is 3. Now we put the value x4 in the third equation. We get x3 as 1. Now x4 is 3, x3 is 1. Now we use the second equation and we can calculate x2, which comes out to be 2. And finally, from the first equation, we get x1 equal to minus 1. If we see this system, it has a unique solution. And from the augmented matrix, we see that rank of the coefficient matrix is 4, as well as the rank of the augmented matrix is also 4. Both are equal, and it is equal to the number of variables. Consider this example, a system of 4 equations in 3 variables x, y, z. We solve this problem by Gauss elimination method using a matrix form, and we see what is the indication that system has no solution. The system of equations can be represented by its augmented matrix given as AB: 1, minus 1, 2, 4. Second row is 1, 0, 1, 6. Third row 2, minus 3, 5, 4. And fourth row is 3, 2, minus 1 and 1. Now we apply elementary row operations and we reduce the system to echelon form. We start with the first row. Its first entry is non-zero, which is 1. So this is the pivot element. Using this, we reduce all the entry in this column to 0. So for this one, I am applying following elementary row operations. Change second row to second row minus first row. For the third row minus 2 times first row. For the fourth row minus 3 times first row. Now using these elementary operations, the augmented matrix is equivalent to the following matrix. First matrix on the slide, 1, minus 1, 2, 4, first row as it is. Now second row is 0, 1, minus 1, 2. Third row is 0, minus 1, 1, minus 4. And fourth row is 0, 5, minus 7, minus 11. Now we move to the second row. Its first non-zero entry is 1, so this is the pivot element. Now using this, we reduce the second entry in third row and fourth row to 0. So for this one, I am applying following elementary row operations. Change third row to third row plus second row, and fourth row goes to fourth row minus 5 times second row. So the augmented matrix is now equivalent to the second matrix here. 1, minus 1, 2, 4. Second row is 0, 1, minus 1, 2. Third row is 0, 0, 0, minus 2. And fourth row is 0, 0, minus 2, minus 21. Now I am interchanging third row and the fourth row in the previous matrix. And finally, the augmented matrix AB is equivalent to this matrix. 1, minus 1, 2, 4. 0, 1, minus 1, 2. Third row is 0 0 minus 2 minus 21, and fourth row is 0 0 0 minus 2. Now this is in echelon form, and from the last row of this augmented matrix we have the following equation: 0 times x plus 0 times y plus 0 times z, this is equal to minus 2. If we see the left hand side, it is always 0 for all values of x, y and z. So 0 can't be equal to minus 2. So this implies that system has no solution. So if we talk about the rank of the matrix, we see that the rank of the coefficient matrix here is 3, while the rank of the augmented matrix is 4. They are not equal. From various numerical problems, we have observed that the system has a unique solution if rank of the augmented matrix is equal to the rank of coefficient matrix, and this is equal to the number of variables. And for a system to have a solution rank of coefficient matrix A, it should be equal to the rank of the augmented matrix. If they are not equal, then system has no solution. So we have one theorem, existence and uniqueness theorem. It says that if we have a system of m equations in n variables with the corresponding augmented matrix M as AB, then system has solution if and only if rank of the matrix A, this is equal to the rank of augmented matrix. The solution is unique if and only if rank of A, this is equal to the rank of augmented matrix, and this is same as n number of variables. From this theorem, we can interpret that system has no solution if rank of matrix A is not equal to the rank of augmented matrix. Now we discuss Gauss-Jordan elimination method. This one is something similar to the Gauss elimination method. The only difference is that in Gauss-Jordan method, we reduce the matrix in row canonical form, whereas in Gauss elimination method, we reduce the augmented matrix in echelon form. Consider the following system of 3 equations in 3 variables x, y, z. We solve this system by Gauss-Jordan elimination method. So corresponding to this system, we write down the associated augmented matrix AB, where the first row is corresponding to the first equation, 1, minus 2, 3, 9. Second row of the augmented matrix is minus 1, 3, 0, minus 4, and the third row is 2, minus 5, 5 and 17. Now we apply suitable elementary row operations and we reduce this matrix to row canonical form. So we start with the first row. The first entry in this row is a 1, which is non-zero. So this is the pivot element. Now using elementary operation, we make all the entries below this as 0. So for this one, I am applying the first operation. Change second row to second row plus first row. And for the third row, we have third row minus 2 times first row. So the augmented matrix is equivalent to the second matrix here, which is first row as it is 1, minus 2, 3, 9. Now second row is 0, 1, 3, 5, and third row is 0, minus 1, minus 1, minus 1. Now we go to the second row. The first non-zero entry is a 1 corresponding to the second column. So this is the pivot element. Using this element, we make the first non-zero entry in third row, which is minus 1 to 0. So for this, I am applying the following elementary row operation. Third row goes to third row plus second row. So we have the third matrix on this slide. First row and second row as it is. And now third row is 0, 0, 2 and 4. Now in the third row, 2 is the non-zero element, so this is the next pivot element. So currently this matrix here is in echelon form, but we have to reduce this matrix to row canonical form. So first I will make the pivot element 1. So we apply elementary row operation, divide third row by 2. After applying this elementary row operation, the augmented matrix is equivalent to the first matrix here, 1, minus 2, 3, 9. Second one is 0, 1, 3, 5. and third row is 0 0 1 2. Now if you see the second pivot element in second row, we have to make all entries 0 except this pivot element. So in the third row, corresponding entry is already 0 in the second column. But corresponding to first row, the second entry is non-zero and it is -2. So we apply the following elementary operation and we make it 0. First row goes to first row plus 2 times second row. Then the augmented matrix reduces to 1 0 9 19. Second row as it is and third row as it is. Now we go to the next pivot element corresponding to the third row, that is 1. I have circled it. Please refer to the second matrix here. Now if we see this third column, except this pivot element, we have 2 non-zero entries, 9 in the first row and 3 in the second row. So we apply the following elementary row operations. Change R1 to R1 minus 9 times R3, and second row is R2 minus 3 times R3, that is third row. Then finally the augmented matrix is equivalent to this matrix. Refer to the fourth matrix here, 1 0 0 1 0 1 0 minus 1, and the third row is 0 0 1 2. We see that here the rank of the augmented matrix is 3, rank of the coefficient matrix is 3, and number of variables is also 3. So the system has a unique solution. We can write down the equations corresponding to this augmented matrix, and from the first row we get x equal to 1, y equal to -1 and z equal to 2. Consider this problem. We solve this again by a Gauss-Jordan elimination method, but the system has infinite solutions. So let's start with the problem. We have a system of 2 equations in 3 variables x, y and z. Here first equation is 2x plus 4y minus 2z equal to 0, and second equation is 3x plus 5y equal to 1. Corresponding to this system, we have the following augmented matrix represented as AB. The first row is 2 4 minus 2 0. Second row is 3 5 0 1. Please refer to the first matrix on this slide. Now in the first row, first non-zero entry is 2. So this is the pivot element. So here I am dividing first row by 2 because we have to make the pivot element as 1. So we get the second matrix on this slide, 1 2 minus 1 0 3 5 0 1. Now refer to the first column. 1 is the pivot element. So except this, we have to make all other entries 0. So we make the first entry in the second row, which is 3 0. So for this one I am applying the following operation. Change R2 to R2 minus 3 times R1. Then the augmented matrix is equivalent to the third matrix here, 1 2 minus 1 0. Second row is 0 minus 1 3 and 1. Now see the third matrix on this slide. In the second row, first non-zero entry is -1. So this is a pivot element. So we have to make this 1. So I am applying suitable elementary row operation. I will divide second row by -1, or you can say multiply second row by -1. After applying this elementary row operation, we get the first matrix here, augmented matrix, with the first row as a 1 2 minus 1 0. Second row is 0 1 minus 3 minus 1. Now this is in echelon form but not in row canonical form. So we have to apply one more elementary operation, because in the first column we have the required format, but in the second column corresponding to second row, 1 is the pivot element, but in this column we have a non-zero entry, that is 2, corresponding to the first row. So we have to make this 2 0. So for this one I am applying the following elementary row operation. Change first row to first row minus 2 times second row. So we get the second matrix here, 1 0 5 2 0, 1, minus 3, minus 1. So now the augmented matrix is equivalent to this row canonical matrix. Please refer to second matrix here. Now from this one, we observe that the first two columns, 1, 1, they refer to x and y variables. So x and y are pivot variables and z variable is the free variable. Now from this row canonical matrix, we can write down the equations. We have following two equations: x plus 5z equal to 2. Second equation is y minus 3z equal to minus 1. If we have a system with well-defined pivot variables and free variables, then its solution can be calculated by assigning random values to free variables, and then we solve the remaining system with pivot variables. So here z is free variable, so I am saying let z be t, where t is any real number. Then using these two equations, we can find out x and y. From the first equation, x is 2 minus 5t, and from the second equation, y is 1 plus 3t and z equal to t. As we change t, we can have different values of x and y, and we can say that system has infinitely many solutions. Consider the following system of linear equations. We have three equations in three variables x, y, z. First one is 2x plus 3y plus 5z equal to 0. Second is minus 5x plus 6y minus 3z equal to 0. And third equation is 2x plus 4y minus 6z equal to 0. If we observe the right hand side of these equations, all are 0. And without doing any calculations, we can clearly see that x 0, y equal to 0 and z equal to 0 is a solution of this system. So this system is always consistent. So now we can start the next one, homogeneous system, the example which we have just discussed on the previous slide. A system of linear equations is said to be homogeneous if all the constant terms on the right hand side are 0, and the system can be represented as ax equal to 0. You can see this system. We have m equations in n variables x1, x2 and xn, and the right hand side term is always 0. So such a system is called homogeneous system. Now what about the feasibility of this system ax equal to 0? Clearly a homogeneous system is always feasible, and 0 vector, that is 0, 0, 0, is a solution of this homogeneous system. Such a solution is called 0 or the trivial solution of the system. We can solve the system by Gauss elimination method or Gauss-Jordan method. So suppose I am reducing these m equations in n variables into the echelon form, and we have the following echelon form. In this, I have r equations in row echelon form, and n is the number of unknowns. So from this echelon form, we can say that x1, xj2 and xjr, these are the pivot variables, and the remaining n minus r variables are free variables. So we have following two cases about the solution of this system. If r equal to n, that is, after reducing the system in echelon form, number of equations is equal to the number of variables, then system has a unique solution, and that solution is 0 solution. If the number of equations is less than the number of the variables, then system has a non-zero solution, and in this case we have actually infinitely many solutions. Consider the numerical problem, example 16. We have to find out the solution of this homogeneous system. It is a system of three equations in three unknowns x, y and z. Now we write down the system in the augmented matrix. Its first row is 1, 1, minus 1, 0. Second row is 2, minus 3, 1, 0. And third row is 1, minus 4, 2, 0. The first matrix here. The first row here we have 1. First entry is non-zero, so this is the pivot element. Now we apply suitable elementary row operations and we make all the entries in the first column 0 except the pivot element of 1 in the first row. So for this one the operations are: second row goes to second row minus 2 times first row, and third row is third row minus first row. So we have the second matrix. Augmented matrix is equivalent to first row as it is 1 1 minus 1 0, second row is 0 minus 5 3 0, and third row is 0 minus 5 3 0. Now go to the second row. Here I have circled minus 5. This is the pivot element. Using this pivot element, I will make the third row's first entry non-zero, that is minus 5 0. So for this one we will apply the operation as third row goes to third row minus second row. After applying this elementary row operation, the augmented matrix is equivalent to this matrix with the first row as 1 1 minus 1 0, second row is 0 minus 5 3 0, third row is 0 0 0 0. Here we see that the rank of the augmented matrix and the rank of the coefficient matrix both are same and they are equal to 2, which is less than the number of variables. So we say that system has a non-zero solution. In fact, it has infinitely many solutions. Here x and y are pivot variables and z variable is the free variable. Now from the augmented matrix in echelon form, we have following two equations: x plus y minus z equal to 0 corresponding to the first row from the above matrix, and from the second row we have minus 5y plus 3z equal to 0. Now we can define z as t, where t is any real number. Then from the second equation we have y equal to 3t divided by 5, and from the first equation we can calculate x using the value of y and z, and x comes out to be 2 by 5. So we have finally x equal to 2t by 5, y is 3t by 5, and z equal to t. This is the general solution of the given system. Here we can assign t any real value. For example, if t is 5, then z is 5, y is 3, and x is 2. So we can say that 2 3 5 is a particular solution of this given system. Consider the following example: homogeneous system, 3 equations in 3 variables. We can write down the augmented form A, B as: first row is 1 1 minus 1 0, second row is 2 4 minus 1 0, and third row is 3 2 2 0. Now we apply elementary row operations and we reduce the system to the echelon form. Here I am not discussing the details of the calculations. The matrix in augmented form is the second matrix here, and it is 1 1 minus 1 0, second row is 0 2 1 0, and third row is 0 0 11 0. Now corresponding to this matrix we can write down the equations as x plus y minus z equal to 0, second row is 2y plus z equal to 0, and third row is 11z equal to 0. So from the third equation we see that z equal to 0, and if z is 0 we can use the second equation, that is 2y plus z equal to 0. This implies that y is 0. Now using that y is 0 and z is 0, first equation implies that x is 0. So the system has a trivial solution: x 0, y 0, and z 0. Now if we see the rank of the augmented matrix, its rank is 3, and rank of coefficient matrix is also 3. Both are equal, so system has a solution. But if the rank of the matrix augmented and the coefficient matrix are equal, and this is equal to the number of unknowns, then system has a unique solution. So using this theorem, if a homogeneous system has a unique solution, then that solution is always 0 0 0. That is a trivial solution. Consider the following system of homogeneous equations. We have three equations in three variables x, y and z. First equation is x minus y plus 2z equal to 0. Second equation is minus x plus y minus z equal to 0. And third equation is x plus ky plus z equal to 0. Here this k is a scalar which we have to find out such that the system has a unique solution. That is exactly one solution, and that solution is 0, 0, 0. So corresponding to this system, we can write down the associated augmented matrix as, refer to the first matrix here, 1, minus 1, 2, 0. This is the first row. Second row is minus 1, 1, minus 1, 0. And third row is 1, k, 1, 0. Now for a unique solution, rank of the coefficient matrix is same as the rank of the augmented matrix, and this is equal to the number of variables, that is 3. So now we reduce this matrix to echelon form by applying elementary row operations, and we try to see the rank of the matrix. So first row, first entry is non-zero and it is 1. Now we make all the entries in the first column corresponding to the second row and third row equal to 0. So for this one we apply these elementary row operations. Change second row to second row plus first row, and third row goes to third row minus first row. So we have the second matrix here. After applying the first operation, R2 goes to R2 plus R1. So I am writing the first row as it is, 1 minus 1 2 0, where 1 is the pivot variable. Now after applying this operation, second row reduces to 0 0 1 0. Now I am applying the second elementary operation, that third row goes to third row minus first row. So using this one we get the second matrix here, and the third row is 0, k plus 1, minus 1 and 0. Now we apply the following elementary row operation. Interchange second and third row in the augmented matrix. Now the augmented matrix is equivalent to this matrix, whose first row is 1 minus 1 2 0. Second row is 0, k plus 1 minus 1 0, and third row is 0 0 1 0. Refer to the first matrix on this slide. Now in the second row, the second entry is k plus 1, where k is any real number. So if k plus 1 is not equal to 0, then the above matrix is in echelon form, and clearly rank of this matrix, coefficient matrix A and the augmented matrix, is 3. It means the homogeneous system has a unique solution, x0, y0 and z0. So we can say that for k not equal to minus 1, the system has a unique solution. Otherwise, if k plus 1 equal to 0, then the augmented matrix is equivalent to the following matrix. See the second matrix here, 1 minus 1 2 0, 0 0 minus 1 0, 0 0 1 0. Now in the second matrix here, the third entry in the second row, that is minus 1, this is the pivot element. Now the matrix is not in echelon form, so we apply the following elementary row operation. Change third row to third row plus second row, and in this case the augmented matrix reduces to 1 minus 1 2 0. Second row is 0 0 minus 1 0, and third row is 0 0 0 0. So finally the augmented matrix reduces to the following echelon form, 1 minus 1 2 0, 0 0 minus 1 0 and 0 0 0 0. Now here rank of the augmented matrix and the coefficient matrix both are 2, which is less than the number of variables. So system has infinitely many solutions. Here x and z, they are pivot variable and y is the free variable. So from the augmented matrix we have the following system of equations. From the first row we have x minus y plus 2z equal to 0, and from the second row of this augmented matrix, we have minus z equal to 0. So this implies that z equal to 0, and if z is 0, then from the first equation we have x minus y equal to 0. Now y is free variable, so we can assign y any real value. So let y be t. Then using the equation x minus y equal to 0, we have x equal to t. So the solution of the problem is x equal to t, y equal to t, and z equal to 0, where t is any real number. So system has infinitely many solutions. You can try these problems for homogeneous systems, find out the solutions of these systems. And the third problem is you have to find out the value of k such that the system of linear equations has exactly one solution. It means we apply elementary row operations and we try to reduce the system in echelon form, and such that we have rank of the coefficient matrix and the augmented matrix is 3. That is the number of variables in the problem, and then try to find out the value of k. So given a system of equations, system may be consistent or inconsistent. If a system is consistent, it means system has a solution. System may have a unique solution or infinitely many solutions. And now here I will discuss about the geometrical interpretation of a solution of a system of equations, and for this we need linear combination of vectors. So here I am considering m equations defined here with n variables x1, x2 and xn, where b1, b2, bm, these are the constants on the right hand side of these equations. Now I can rewrite the system of equations in the following form, that the coefficients of variable x1, I can rewrite these in the form of a column vector. So see the next expression here, x1 times a column vector and its elements are a11, a21, am1, plus x2 times another column vector, and these are the coefficients of x2 in these equations. So it is a12, a22 and am2, and so on. We go up to xn and its coefficients are a1n, a2n and amn, and on the right hand side we have column vector with entries as b1, b2 and bm, where all these x1, x2 and xn are real numbers. Now we try to see what exactly is this expression on the left hand side of this equation when we are writing the system of equations in vector form, where we have x1, x2, xn, and we are multiplying these variables by these vectors with entries as the coefficients of these variables in the system of these equations. Let capital A1, capital A2 and capital AN belongs to Rm. These are column vectors. Then a linear combination of these vectors is an expression defined as C1A1 plus C2A2 plus so on up to CNAN, and this one again is a vector in Rm, where this C1 and C2, Cn all are real numbers. So such a combination is called linear combination of given vectors A1, A2, An. Let capital A1 be the vector defined as a column vector with entries as A11, A21, Am1. So we can say that this is the column vector representing the coefficients of variable x1 in the system of linear equations. Similarly, A2 is A12, A22 and so on up to am2. So this is the vector representing the coefficients of variable x2 in the system of equations. Similarly, we have an as a1n, a2n up to amn. So the given system of linear equations can be represented as x1 capital A1 plus x2 capital A2 plus so on up to xn capital AN, this is equal to capital B, where capital B is the vector of right hand sides, that is B1, B2, Bm. So we can say that a system of linear equations has a solution if the vector B, that is B1, B2, Bm, can be written as a linear combinations of column vectors of the coefficient matrix A, that is A1, A2 and An. If there is only one such combination, then we say system has a unique solution, or if there are more than one combination, then we say system has infinitely many solutions. And if it is not possible to write a B vector as a linear combination of this coefficient matrix, then we say that system has no solution. So we will discuss numerical problem to see this thing. For geometrical interpretation, I am considering this example, a system of two equations in two variables x, y. We have two equations as x plus 4y equal to 7 and 2x plus 2y equal to 8. This system has a solution as x equal to 3 and y equal to 1. You can just draw it geometrically, and these two lines, they are intersecting at a unique point. That point is 3, 1, because these two lines, they have different slopes. So I can write down the system in the form of vectors. It is x times a column vector with entries as 1, 2 plus y times the next column vector with entries as 4 and 2. This is equal to 7, 8. So if this system has a solution, it means we want to find out this fact. Can we write vector 7, 8 as a linear combination of following two vectors 1, 2 and 4, 2? If we can find out any such combination, then we say that yes, system has a unique solution. If it is not possible to find out any such combination, then we say that system has no solution. But we know that 3, 1 is a solution of this system. So we will see that we can write down 7, 8 vector in a unique way as a linear combination of these two vectors 1, 2 and 4, 2. Now we draw these vectors, capital A1, capital A2 and the vector B on this graph. A1 is 1, 2. I am representing this by red dot. Then I have A2, that is 4, 2. This is the red vector here. And the right hand side vector B, that is 7, 8. So now we want to see whether we can write down this vector B, which is 7, 8, as a linear combination of these two vectors, capital A1 and A2. We know that the sum of two vectors is given by the diagonal of the parallelogram, whose two sides are these vectors A1 and A2. So we try to see whether we can write down this vector B as a linear combination of A1 and A2. So we will try to make a parallelogram using these vectors, capital A1 and capital A2. We know that the solution of this problem is 3, x is 3 and y is 1. So what I will do, I will draw a vector which is 3 times a1. So a1 is 1, 2. So the vector 3 times a1 will be 3, 6. So I am representing this by a dot. We can see the graph here, 3, 6. Now I have two vectors. One is 3 times a1 vector and second one a2 as it is. This is 4, 2. Now if we complete this parallelogram whose two sides are 3a1 and a2, then we can see from the graph that its diagonal, it is exactly same as the vector b. So I can say that vector b 7, 8 is the sum of two vectors 3 times a1 and a2. So if we are able to find out a parallelogram by using these two vectors a1 and a2, you can multiply these vectors a1 and a2 by any real number, positive, negative, depending upon the solution, and we can have more solution also. So in that case, if it is possible, we say that system has a solution, and geometrically we can represent this vector b as a linear combination of these two vectors, capital A1 and A2. I'm discussing one more example where the system has no solution. Then what will happen geometrically? Then logically, the right hand side vector cannot be written as a linear combination of the vectors of the coefficients of x and coefficients of y. So here we have these two equations, x plus 2y equal to 6 and 2x plus 4y equal to 7. We can see that these two equations, they have same slope but they have different y-intercept. So these two equations are parallel lines, so they will never intersect, so system has no solution. Now we will see this thing geometrically in terms of linear combinations. Here the first vector containing the coefficients of x is 1, 2, and with the coefficients of y we have 2, 4. I'm representing that by A2. So you can see the graph 1, 2, this is the given vector A1, and then 2, 4, the second vector A2. Here the right hand side vector is 6, 7. So now we want to see whether this system has a solution or not. If the system has a solution, in that case we must be able to write down 6, 7, that is vector B, as a linear combination of these two vectors A1 and A2. It means we must form a parallelogram using these two vectors A1 and A2 by multiplying them by suitable scalars such that B becomes the diagonal of that parallelogram. But if you see the graph, A1 and A2, these two vectors, they are in the same direction. So even if we multiply them by some positive scalars or negative scalars, either they are in the same direction or in opposite directions. It means they will never form a parallelogram. This implies that we can't write B as a diagonal of the parallelogram in terms of vector A1 and A2, so we say that system has no solution.